Hello, I am Jin Meng from Georgia Tech. Now I present sliding window QPS, a perfect parallel iterative switching algorithm for input-queue switches. Input-queue switches are cheap and widely used. In such switches, the arriving packets wait at the input ports before entering the switch. Each input port has n virtual output queues, or VOQs. For example, VOQ1 of input port 1 stores all the packets that goes from input 1 to output 1. We will use the length of these VOQs in our scheduler. We further assume that we only deal with fixed size packet segments, and that all the input ports, output ports, and the crossbar operate at the same normalized speed 1, so there is no speed up. The crossbar has a constraint that during each time slot, each input port can only connect to at most one output port, and vice versa. We model this constraint with a bipartite graph model. In this model, the input ports and the output ports are two disjoint vertex sets, and each valid crossbar schedule corresponds to a matching in this bipartite graph. So the objective of the scheduler is to compute high-quality bipartite graph matchings. By high quality, we mean this matching could achieve maximal throughput and minimal queuing delay. This is a challenge because each matching is needed for each time slot, but the duration of the time slots is really short for modern switches, but the number of input and output ports is getting larger and larger. For example, if in order to achieve the 100 gigabits per second line rate as in Tomahawk 4, the scheduler has only 10 nanoseconds to compute a matching between as many as 256 input ports and 256 output ports. Furthermore, the scheduling algorithm should be simple enough to implement in hardware. There is a well-known trade-off between the quality of the matching and the time needed to compute the matching. So it is really difficult to compute high-quality matchings in small time with a large number of input and output ports. On one side, if we have no timing constraint, maximum weighted matching is a good choice. It achieves near optimal empirical performance, but the complexity is too high. On the other side, we may turn to parallel iterative schedulers to meet the strict timing constraints. For example, iSleep is widely used in switches, and QPS1 produces each matching in O1 time. But the quality of these produced matchings is far from optimal. Here is our roadmap of this research. At first, we present small batch QPS. It converts QPS1 to a batched scheduler. The main contribution of small batch QPS is that it achieves high throughput with a batch size that is much smaller than previous batch schedulers. Next, we present sliding window QPS. This is the final result of our research. It inherits all the benefits of small batch QPS, but pays no batching delay. We start with QPS1 because both of our schemes are based on it. QPS1 computes each matching in the following two stages: in the proposing stage and an accepting stage. In the proposing stage, each input port proposes to a randomly sampled output port. The probability that each output port is sampled by input 1 is proportional to the corresponding VOQ length at input 1. Using a QPS algorithm, this sampling can be performed in O1 time. In the accepting stage, each output port accepts exactly one proposal with the longest VOQ length. Because multiple input ports may propose to the same output port, only one of these proposals can be accepted. So the throughput of QPS-1 is far from optimal. We try to solve this problem in small batch QPS by combining every T matchings into a batch. A batch is computed in multiple rounds of proposing and accepting stages. In this work, we use T rounds for each batch, so the amortized complexity is 1 round per time slot. This is the same as in QPS-1. The proposing stage of small batch QPS is almost the same as in QPS-1. The only difference is that each proposal includes the availability of the proposer during each of the T time slots in the batch. In the accepting stage, small batch QPS attempts to accept all the received proposals if possible to maximize the throughput. When multiple proposals are received, the output port first sorts them in descending order of VOQ length, and then attempts to accept them one by one on the first commonly available time slot. This is the first time slot in the batch when both the proposer and the proposee are unmatched. The first commonly available time slot is computed using the availability of the proposer and the proposee. For small batch sizes, the availability fits in a machine word, so the first commonly available time slot can be found in one instruction. Therefore, the time complexity of both the proposing stage and the accepting stage of small batch QPS is a 1. Small batch QPS achieves high throughput with small batch size, but it pays a non-trivial batching delay of T time slots, since it generates a batch of T matchings every T time slots. So we designed sliding window QPS to avoid paying this batching delay by generating one matching during each time slot. This is the only difference between small batch QPS and sliding window QPS. The schemes in the two stages, proposing and accepting stages, are exactly the same. Here, we show how sliding window QPS generates the one matching each time slot using this animation. Here is a batch of capital T time slots and capital T matchings. Each matching is a column in this figure. As time slot lowercase t, the first matching in this batch is scheduled, and we add a new empty matching to the end of this batch, so that this batch always contains capital T matchings. At time slot t plus 1, we perform the same operation. The first matching is scheduled, and a new matching is added. As this batch slides forward in time, each matching stays in this batch and can be filled with proposals for capital T time slots. This is the same as in a static batch as in small batch QPS. Here we show the empirical performance of our schemes in simulation. We model the arrival of packets as an independent Bernoulli arrival process and generated 4 different traffic matrices. We used 64 input and output ports and a batch size of 16. This table shows the maximum achievable throughput of 4 schemes. From this table, we can see sliding window QPS achieves higher throughput than small batch QPS and QPS-1. It also achieves higher throughput than iSleep, except under uniform traffic. Although sliding window QPS only uses 1 round for each matching, but iSleep needs all log n rounds to compute each matching. Here n is the number of input and output ports. This figure shows the average queuing delay under different normalized traffic load levels. From this figure, we can see sliding window QPS achieves lower queuing delay than small batch QPS and QPS-1. It also achieves lower queuing delay than iSleep except under uniform traffic. In conclusion, we propose small batch QPS. It achieves high throughput with a small batch size. And we propose sliding window QPS, the final result of this research. It inherits all the benefits of small batch QPS and avoids paying the batching delay. Thank you.
Recording has